All right, electron configurations. In these notes, I'm not going to show you actually how to write an electron configuration. I did that in the example in your digital notebook, but I am going to take you through like the governing laws. You can also read about those in your book in the outline that will be assigned for that. Um, so the goal of every electron is to um, I guess like reach their most possible ground state. But electrons or how energy levels are filled is with a maximum amount of energy of electrons based on the what's that called on the number of electrons in the energy level. So our first energy level can have 2 electrons. Our second energy level can have up to 8. Our third energy level, it depends on the atom. Sometimes it's 8, sometimes it's 18, but you'll kind of see that when I go through the example. But here is an example of what a electron configuration looks like. So the number here, so 1, 2, 2, 3, 3, 4, 3, those represent energy levels. So like I said, in their most ground state, they fill the energy levels in order. So energy level 1, I just said that it could have 2 electrons. And so these 2 electrons, or this number 2 here represents how many electrons. So in energy level 1, I have 2 electrons, and then the letter is sort of like the shape of how those electrons travel or their path. We call that an orbital. So this would be energy level 1, orbital S, and then there's 2 electrons traveling in orbital S on the first energy level. Then we move on to the second energy level, and we have an S orbital and a P orbital. The s orbitals can only hold 2 electrons. So even though energy level 2 can hold 8 electrons, the first 2 are in the s orbital, and then the other 6 are in the p orbital. Then I move on to energy level 3. So energy level 3 can contain up to 18 electrons. So only 2 can fit in S. So we have the 2 represented in S on energy level 3. Only 6 can fit in P. So we have the 6 represented in P on energy level 3. And then we can fit 10 on energy level or on the orbital D in energy level 3. So it's written in this order because that's how you write it off of the periodic table. Again, you'll see that in the example. But if I'm just evaluating it, I can see that I have level 3 here, here, and here, and that's a total of 18 electrons, 10 here, 6 here, and 2 there. So I can repeat that with energy levels 4 and 5 and so forth. This down here we call the noble gas configuration. It just means that as you're going through and writing your um, your uh, electron configurations, this is sort of the like shorthand where you could skip to the noble gas that is before whatever element it is that you are taking a look at, and you can write the electron configuration starting at that noble gas. So when it has these brackets, it means that the electron configuration for xenon comes before all of this, which is the rest of the electron configuration for lead. So there's 3 main governing rules for how to do it, and you can't really violate these rules. So first rule is Aufbaus Principle, and it says that electrons occupy the lowest energy level in energy orbital. So this is in your book. I think sometimes it's helpful for people and sometimes it's not. But energy levels are listed here along with orbitals, and you fill in this direction. So you hit the lowest energy orbital first, then you would hit the second lowest energy orbital, and then the third lowest energy orbital, and then the fourth, and so forth. So you would basically be filling orbitals in this order. I think it's easier just to use the periodic table, but that's what Aufbaus Principle is saying, is that the lowest energy orbital needs to be filled before you can move on to the next one. Pauli exclusion says that no 2 electrons can have the same 4 quantum numbers. So quantum numbers you'll learn about a little bit later, but there are 4. There's the principal quantum number, which is represented by the energy level. So it's represented by the 1, 2, 3. Those are the principal quantum numbers. The angular momentum is the letter. So is it in an s orbital, a p orbital, a d orbital, or an f orbital? Those are our four orbitals that are like known right now. um, the magnetic um, quantum number basically is the specific electron and I guess like where it's sitting within an orbital, and then the spin is showing that the electrons are going different directions. There's no, there's, it's not a value, but if you were to look up a value in the book, it would say like plus or minus a half. It just means that if one electron is spinning clockwise, then the other one that's in that same energy level in the same orbital is going the other direction. So if I look here at 1s2, I have two electrons. Both of them have the same principal quantum number. They both have the same angular momentum number. They both have the same magnetic number because there's only one configuration for S, but they have different spins, one spinning clockwise, one spinning counterclockwise. That's kind of how we differentiate. Oops. And then two, so when we say that they must have different spins, there's orbital notations down here. So you guys saw these are electron configurations. This is the noble gas configuration, which is just a shortened one, but we also do orbital notations, which shows electrons going different directions. So like here where I was just talking about the 1s2, there's only one configuration for S, so the energy level is the same, the angular momentum is the same, magnetic, which is like the orientation, there's only one, so that's the same, but these electrons are spinning different directions. So the different directions here is the Pauli exclusion principle. If these were both had an upward spin, if it was two arrows pointing up, you would be defying Pauli exclusion because those two electrons would have the same four quantum numbers. I showing you in magnetic here when you're looking at the orbital notation like this, we have the 1s down here. Again, S only has one orientation, so 2s, S only has one orientation. P actually has three orientations. So that's like the magnetic, it's like the orientations. D has 5 orientations and F has 7, which is why you can fit double the amount of electrons in there. So S has one orientation, it can fit 2 electrons. P has 3 orientations, it can fit 6 electrons, right? Because it could have 2 on each orientation just going opposite directions. D has 5 orientations, it can fit 10 electrons, and F has 7 orientations, and it can fit 14 electrons. Hunds rule is the last one, and it says that each orbital in the same energy level must be occupied by one electron before any orbital can occupy a second electron. So for S, this doesn't really, it only has one orientation, so this rule doesn't even really apply to S, but it does apply to P, D, and F because P, D, and F have multiple orientations. So here's an example of a correct and incorrect way to write your orbital notation for an electron, for doing electron placement. So here we have the p orbital. Again, it has 3 orientations, which means it can fit 6 electrons. But if you don't have 6 electrons to fill it up, then each orientation needs to get 1 electron before any orientation can get a second. So if you had 2, they would be split up in different orientations. That's because electrons are negative, and so they repel each other. They want to be as far apart as possible. So that's why they're going to fill different orientations before they both get stuck in the same one. So this would not occur, leaving 2 orbitals, 2 orbital orientations open with no electrons in it and then shoving 2 into 1. That wouldn't make sense. Electrons want to be as far apart as possible, so each one of these orientations would need an electron before the one orientation could have a second. So if you have P, they're all going to be half filled until you get that 4th electron. That 4th electron would then fill one, if a 5th electron would then fill another, and then the 6th would have them all completely full. Here's just another example of like correct ways to write these for Hund's rule. So again, we wouldn't write it like this. Every orientation needs 1 electron before any orientation can have a second. So this electron would really need to be in this 3rd box. It also needs to have the same spin. So the electrons, like the first electrons will all have the same spin. The second electron is the one that gets it the opposite direction. So C would be the correct way to write 3 electrons in a p orbital. And again, that's only if I have you writing orbital notation, which is how you show the direction of the electrons. This part down here where it says 1s2, 2s2, 2p2, that's the electron configuration. This here where you're drawing the arrows to represent electrons is called orbital notation. And that's it. Please let me know if you guys have any questions. Move on to the notebook. Make sure you are watching the examples for how to write an electron configuration before you start the assignment. Thanks.